Okay, good afternoon. So we're going to continue with some more precise details about variational data assimilation. To begin with, I'll be quite reasonably short, so we can move on also to the statistical data assimilation, which is the second big category of methods used for data assimilation. I'll tell you also that in fact the methods used for statistical data assimilation are also used for many other applications, not just for data assimilation, but used for many things. Okay, so you remember the whole idea is that we have some kind of model trajectory, which is the green line, and as soon as observations come in, the idea is to correct the model trajectory to get an analyzed state, and from that analyzed state, which we call, if you like, the initial condition or the background condition, we project forward and we get to a better state, which is the red line, which follows more closely the observations, whereas the green line goes where it goes. The red line, which is corrected, the analyzed state, does an optimal interpolation in some sense between two terms in the cost function, which is a background term, and an observation term. So we take into account the background, and we take into account the fact that we have observations, and then we do some optimization. I showed you how to do it in a simple case, and that extends very easily to the general case. So I'll show you very rapidly how it extends to the general case. So basically, we have a state equation. Now this can be any equation. You see, I'm not limiting m of x. I'm not saying it's reaction diffusion, or it's this or that, or Navier-Stokes, or it's whatever you like. It's a completely general theory with an initial condition. All I give is a domain in space omega and a time interval. And what is important, I told you to run. Just wait, I must switch off. I must mute. Oh, no, I am muted. Okay. It's not me. The feedback is a type of control. Okay, so we need a cost function, and you see this cost function takes into account two terms, what we call JB and JO. I could say J equals JB plus JO. JB is the background term of the cost function, and JO is this part, is the observation part. So you see, I'm trying to balance between background, which means the previous guess. The background is the initial condition of the actual time step, which, if you like, it was the analyzed state of the previous time step. We project forward, we stop, we use where we reached as the new condition, but we take into account the fact there's an error here, or C, here also for hx minus y. H is just the operator that says we don't observe x everywhere, so we should have an operator that takes into account the fact that we have observations at certain points, and this R represents the fact that we might have errors, random errors. We quantify them here in our measurements. The B takes into account the fact that we have some kind of random error inside our analyzed state, between the background state and X. And so we just have to go and minimize this guy, all right? So, we know how to do that. Okay, let me just rapidly say the different terms that we've seen so far. I said notation is important, but I've said these already. X, B, and Y are the state, background state, and measured state respectively. H is the observation matrix. You'll notice that we're going to convert this to a matrix vector form. It's a linear. If there's an observation operator that is non-linear, eventually we can linearize, and then R and B are these two background error covariance matrices that are usually obtained by previous experience. In other words, from previous measurements, we have a lot of measurements, we can estimate their different mechanisms, different techniques, quite simple, to estimate these two matrices. So we have to have some initial, it's some previous knowledge based on experience, in other words, based on previous measurements or previous models. So a lot of trouble and a lot of problems are created by bad estimations of R and B, but eventually one gets better and better. In the end, R and B are very often diagonal or close to diagonal matrices. In other words, things that are far away have less correlation with things that are close to each other, and what's close to each other are the ones that are on the diagonal of these matrices. So they're basically diagonal matrices, sometimes with what we call an exponential spread around the diagonal And it's just a matter of using, finding the coefficient for the exponential spread. So the values, as you move away from the diagonal, get smaller and smaller. Okay, so we cannot really take into account the fact that the systems have unknown parts and errors in the measurement, errors in the propagation, unless we can define these matrices. So these matrices become defined in one way or another. Okay. Okay, we also have to be able to invert these matrices. We'll see, because there's an inversion, and sometimes this cannot be obvious, but okay, there's many problems. Okay, so what we've seen is we have a sum of the weighted background deviations and the weighted observation deviations. So that's the secret of variational data assimilation, that we have both the measurements or the predictions and the observations that are taken into account. Okay. So what happens, in fact, is that when the background, with that epsilon b is our measure of the observation of the background error, and together with observations hx plus epsilon o, that's for the observation, we have them that we've acquired over time, or a short enough interval where the dynamics can be considered stationary, because 3D var is basically a stationary approximation method, whereas there's an extension to a time-dependent method, which is called 4D var. I'll show you very quickly at the end, but it's it's not very simple, but it's relatively simple generalization of the 3D var to extend it to, you remember in the graph that I showed you at the beginning, the 3D var is just at one point where we consider the dynamics doesn't change very much, because we won't use the dynamics equation directly in the analysis here. So in the analysis so we produce an estimate of the system state at time tk, and not over an interval. Oh, that's the difference. 4D var, which is the extension of 3D var to a time-dependent case, will produce an analysis over a time interval and not at a single point in time. Okay, this is a small difference. In fact, in numerical weather forecasting and weather forecasting, up till now, it's been mostly 4D var, but now 4D var is being phased out, and I'll speak to you about it. And we're using more and more what we call statistical methods. Okay, but in the end, the basic methodology is just a gradient descent algorithm, which is a very, very basic, which your first course in numerical optimization, if you do it and if you don't do it, even theoretically, it's very simple. We've got a gradient. We initialize with k equals 0. We suppose we have x equals x0. And while the gradient is large, or we've reached the limit of the number of iterations, in other words, we don't want to spend more time computing, we compute j, we compute the gradient. We use a gradient descent algorithm, any type. It can be simple or more sophisticated, like a quasi-Newton method. We update x to xk plus 1, and then we loop. And so 3D var is basically very simple. We just have to use the stuff that I showed you before. Okay, so just very quickly, I'll show you how you obtain the optimal update in this case. And it's a very simple. It's classical. It's classical functional optimization, which is just a generalization of optimization of a function of f of x. So we suppose that the analyzed state, if you remember, the analyzed state is going to be an optimal interpolation of some sort between where the background projects us, where the initial data projects us, and to where the observation comes, and we want to do something intelligent between the two, right? So let's call xa the argument, in other words, the value of x for which j of x attains a minimum, right? Then the gradient of the cross function, you can just take the cross function on the other slide, and you can see just differentiation of vectors is just a rather simple extension of differentiation of scalars, and you see that the differentiation gives you this expression. We know now from the same as in classical calculus, it's the same in variational calculus, to find the minimum, set the gradient equal to 0, and solve. You solve, and we find that xa must be equal to xb. In other words, xa, you remember, it's my argument. It's the value of x, which gives us the minimum value of the cost function. And you do this it's simple, and you get xb plus k times y minus hxb. So y minus hxb is a well-known It's the error in the measurement, error between what I think I have and what my real observations. This is called, we call this, it's called the innovation. And what is the value of k? Well, k is just done by solving, and you see it's very easy. K is a rather complicated expression, B inverse plus H transpose R inverse H, all inverse times HT times R inverse. So you see, there are a lot of matrices to invert, and in particular, it's this inversion, which is troublesome because B and R are basically close to diagonal matrices, but they can be very large, because they're over space and time. They could, I told you, in numerical weather forecasting and in climate forecasting to evaluate global warming, these matrices are huge, 10 to the 9, 10 to the 10 lines. So they 10 to the 9 times 10 to the 9. Huh? Okay. So we want to avoid, but there are tricks that enable us to avoid, and one of the tricks is what's called the Sherman-Morrison-Woodbury formula. So we can reduce this. You see, here I have R plus HB, HT. The advantage here is that H, this term now is only, and R, these are only the dimension of the observation vector. They have much smaller dimension than the dimension of the state vector. So this guy is much easier to invert because it's much smaller. It's only dimension of the observations and not the dimension of the complete state. Whereas in the previous formula on the other page, I won't go back, we're a dimension of the state, and the state dimension is too high. So, okay, so we have an innovation term. We have the gain matrix, which is rearranged according to this famous formula that you can find in books on numerical linear algebra. And then this linear combination of a background term. So it's basically, it's a linear combination of a background plus an analyzed state, you see here. Okay. This is just a linear combination, this thing, xb plus k times y minus hx. So basically, and this is a classical result from what's known as optimal control theory. So it's very nice because it's the theory of dA actually goes back to optimal control theory. So it rests on something that's very well known. And optimal control is, as I told you, it's calculus of variations. It's the generalization of regular minimization. We want to minimize quadratic functions to the fact that we're not minimizing with respect to a scalar variable x, or even with respect to a vector, but we're minimizing with respect to a function. Okay. Anyway, just to say that this is theoretically very solid. Okay. So, in fact, what I wanted to show you is that this formula here for k, it's nothing else but the generalization of what we saw on the second day, that is the ratio of the background error covariance divided by the sum of the background and the observation error covariance. So I thought, it would be unfortunate if this wasn't the case, but we can show just by observation that this formula here, this formula for k, and this guy here, it's nothing but the generalization of the ratio of variances, and we've shown that the ratio of variances gives what is known as an optimal estimator in a statistical term, in a statistical sense. It's called the BLUE, the best linear unbiased estimator, which is a well-known concept in estimation theory, which is part of statistical analysis. Okay, so just to show you that whatever you do, you get something that does what it should do, thanks to the fact that we take into account BNR, which we don't do any propagation of BNR, but we have to have some constant values that express what we believe are the errors in our background and in our observations. We obtain the generalization to a general state space with a general dynamic system. Okay, and that's basically 3D var. Yeah, okay, I won't do it again, but I just put it in. We've seen this before. This is exactly the same as what we saw on the second day, which says that the best way to estimate the state is to take a weighted average of the background, of course sometimes called the prior, and the observations of the state, And the best weight is the ratio of the mean squared errors or the ratio of the variances. So the variational approach, here we did variational calculus. It's enough, I didn't do any statistics that you saw. I didn't take any expectations. I didn't take any variances. I used pure, simple. Calculus of variations, which is the extension of simple functional of minimization of functions, which is the basis of calculus. Okay, and so this shows that the statistical viewpoint and the variational viewpoint are exactly reduced to the same thing. Okay, then to go a bit further, but here I won't spend time because we'll never finish the program, right? So the next point is that you can extend 3D VAR to what's called 4D VAR, and then 4D VAR, the difference is now that we're going to predict over a time interval and not just at a single time. The 4D VAR takes into account the fact, does the work over a certain time interval, okay? And basically, it's more realistic, but more complicated, because we want to assimilate observations that are required over an interval, during which the system dynamics cannot be neglected. In the case of 3D VAR, we assume that the interval over which we do the assimilation is an interval in which the dynamics of the system don't have an influence. So here we'll have to take into account the matrix M. Before, you didn't see the matrix M appearing at all, but in the 4D VAR, we have to take into account the matrix M. We have the same kind of situation with the observations, observation with an error matrix, but you see now R can depend on K. Before I just had R. Why is R subscript K? It means that R can depend on the time. So I can have also my errors evolving in time. So that becomes more and more realistic. Okay, then the question is, how do you evolve your errors in time? But there are a lot of research that's been done into these. And in many domains, we know how to evolve the errors in time as well. So we have a system which not only takes into account errors, but takes into account that, you know, the wind is blowing now, and then suddenly it blows stronger, then suddenly later it blows less strong, or with less, you know, strong, but with smaller fluctuations, or not so strong with larger fluctuations. So we have what are called non-stationary statistics or stochastic processes. And these algorithms, 4D VAR, 3D VAR, these methods take into account the fact that things can change over time. And of course, we're getting closer and closer to reality, yeah? If that's what we want, right? Okay. Suppose that reality is interesting. Okay, so anyway, one adds the dynamics equations, and then we have the generalization of the objective function. So now we have to sum over the instance of this is the interval of time, k equals 0 to k. K is the index, which indexes the time. And so things become a little bit more complicated. You see, because I've got H can depend on k, R depends on k as well. And there we have the initial P0. We use P for the covariance matrix of the background errors, okay? And then the minimization provides the initial condition that we're looking for. As I said, we're looking for the initial condition. And this analysis is called it's known as strong constraint 4D VAR. Okay, there are many variants of this. I won't go into them. That becomes rather technical. Over the years, there are many variants, and it becomes more and more complicated, but the basic message stays the same. Okay. What's great, what's interesting also, just to make life a little bit more, life isn't complicated enough. One can also include model uncertainty. So we haven't spoken about model uncertainty. Model uncertainty is a big question, because our models never completely simulate or capture the reality of remember I showed you in the first day, when we're looking at environmental problems in natural systems, if we want to take into account and reach a level of detail that is sufficient, there are many things going on. It's not just, you know, nature doesn't just do reaction diffusion. It does reaction diffusion plus heat transfer plus some kind of chemical reaction. So ideally, one should include a lot of other stuff inside our models. Often what we do is we try to include the terms or the unknowns that seem to be the largest and the most important, and we say the others are lower order. But if we need to take into account lower order terms, because we're looking for some kind of unusual behavior, because the extreme behaviors that we're interested in, then we can put a term which tries to capture our lack of knowledge in the model. So we're admitting, this is good. I like it as honest. I like honesty, right? That we don't know everything, and even our model, we think, we've got Navier-Stokes, we've got reaction diffusion, we've got this, we've got that. But in fact, maybe the model is not, and usually the model is not exact, because natural systems and any living system in particular has a number of different models. It's multi-model, multi-scale, whatever. And here we can take this into account as well. So that's one of the advantages of 4D VAR. We can take into account errors or uncertainty, sometimes it's called, in the background, in the observation, and in the model. Okay, just to show you that if one day you need powerful tools for complicated problems, we have them, right? And then J of X becomes more complicated as we go along, right? So here you can see the dynamic equation, or the innovation xk plus 1 minus mk xk, as appearing also in the cost function, okay? And then, okay, it's a function of the complete sequence, and the minimization is known then as weak constraint 4D VAR. So the weak constraint is when we include model error, okay? So just to say, okay, it's not enough. I said I was taking care of uncertainty, or the model can take care of uncertainty. Up till now, it's just been in the background and in the observations, but we can add also the model and model uncertainty. So in the end, we get a system that can really do an excellent job of capturing weather and climate change. And if you understand it, we need models that can do this, to do what's called real-world data assimilation, okay? Okay, traditionally they were all developed, as I said, in meteorology, numerical weather forecasting, and oceanography. These have been the two major groups. Been used a lot for air pollution also. It can be used for predicting air pollution, because air pollution is just a lot of it is based on Navier-Stokes, and in oceanography also other equations, but Navier-Stokes, whether it's in the water or in the air, it can be used also for predicting movements of pollution, etc., etc. So it's used a lot to model air pollution over cities. If you're looking at smart cities and you want to regulate the traffic so that certain zones will be less polluted than others, by doing a simulation, data assimilation based on Navier-Stokes, we can get information about air pollution, for example. So something that's been looked into for smart cities, for example. Okay, but there are a lot of many more problems today being solved or attempted to solve by data assimilation methods. I just mentioned a few, but there's a lot. Okay, but in the real world, of course, assimilation is performed on nonlinear models. For the moment, everything I've shown you, it's in state space form, and these are linear models. It's xk plus 1 equals m multiplied by xk. M can also depend on k, or on k plus 1. We can have non-autonomous systems, but basically they have to be linear. But in fact, there's this non-linearity, and then, but as long as that non-linearity is not too large, these variational data assimilation methods will still produce very useful results. So as it is, it's already, and then the algorithm is very similar to what we had before, except that now we have to compute J using the model M and H, and compute the gradient. We'll have to use an adjoint model now, which I spoke to you before, which will require computation of the transpose of M and the transpose of H, and then there's a gradient descent, and then we go around until we converge. So it's 4D VAR is just not a simple generalization, but it's a generalization. It reduces to 3D VAR when we stop going over a time interval. Okay, this is just some other rapid explanations that just to show if you want to go into the details. Okay, about the gradient, you see the computations become more complicated. And anyway, this is the kind of algorithm that you never program yourself. It's a bit like the finite element method. one uses existing programs. So, and I'll show you some of the results that I've obtained using existing programs in what follows now. So one of the favorite, we call it a toy model, but it's not really such a toy model that's used for complicated environmental phenomena is the Lorentz system. Lorentz was, I think he's still alive, who works in MIT, and he developed a very, very known nonlinear model, toy model, simplified to some extent, for nonlinear chaotic systems. So the whole idea of weather prediction, for example, there's the famous butterfly effect. You've heard about the butterfly effect. Lawrence, I think it was Lawrence who said, the fact that a butterfly flaps its wings in Brazil, can it cause a tornado in Texas? Okay, so this is the famous thing. And if we simulate, here's the system. The system is a very simple system. It's a system of three. There are more complicated Lorentz systems. So the simplest one is the system with three equations, three nonlinear equations, ODEs. Okay, and for a certain combination of sigma, rho, and beta, which are the three coefficients, one really obtains chaotic behavior. So we have chaos. This is really chaos. We have what's called pitchfork bifurcations and period doubling. It's really, you can create, I don't know, fractal, it gives some kind of fractal image in the phase plane. It's a beautiful equation, but you can do many things with this. And it has two orbits, two attractors. These are called attractors. And the system moves from one attractor to the other. Instead of usually a system of ODEs, we want it to be stable, it'll stay around one attractor. But here, chaotic systems are characterized by the fact that they can have multiple attractors, and the system, we don't really know the system's going to be in this state or in this state, because it switches every now and then. And chaotic systems are not unpredictable because they are deterministic. There's nothing stochastic here. It's a deterministic system, but it has the property of being very sensitive to a small change in the initial condition, can give you a very big change in the solution, okay? So it's not stable, chaotic systems are not stable to small perturbations in the condition. You don't know, you change a little bit the initial condition of this equation, and you can go from there to there. So you're not keeping the fact that small changes in conditions lead to small changes in the solution. So that's a chaotic system, and it's used very often as a model for complex dynamics, such as we find very often in the ocean, in the atmosphere, in weather, and in many, many other phenomena. So it's a good toy model to test. Okay. So let me show you very quickly. I did a 4D data assimilation on the system, but I just took an observation term just for simplicity. There's no background term. I could add a background term. It wouldn't make much difference. Just to show that I added just the observation term. So remember, J was equal to JB plus JO. Here I've just taken J equal to JO. Okay. But with this system, you can already study a number of important effects and answer a number of important questions. For example, what is the effect? What is the influence of noise in the observation? You can play with the value of R. It's the observation noise. See how observation noise affects the simulation. You can check out what the influence of the initial guess is. You can check what we call the length of the simulation window and the number of observations that you have. You can check when you have more observations, are your simulations more exact, precise than others? We know they're exact because we can simulate the solutions of the Lorentz system as it is, and so if we try to predict them, we can tell what's happening. So I give the reference to these codes. The code that I use here, because I don't pretend that I can write a code of 4D values, or quite complicated. It's a code that comes from the UK Met Center, or Meteorological Center, which is Reading. They put a lot of their codes now. They're not the only ones. There are many codes. I gave a list on the website, and maybe on the website. There are a lot of codes available. It uses an adjoint approach based on an Euler method, which is a very simple method for solving the ODE system. And we do what are called twin experiments. In fact, we don't have real observations here, right? So what we do is we generate observations which are noisy, and then we ask the system to try assimilate In other words, predict forward as in an optimal way the trajectories of the system using the noisy observations that we generated ourselves. And because we generate them ourselves with the same, because we know the system, right? So we could, it's called a twin experiment. This is a classic way of testing new methods and testing how methods work and learning how methods work. So anyway, here are just for reference, these are the conditions that I used. I used a certain initial condition, a certain initial guess, which is reached 20% distant from the initial condition, time step. I will have an assimilation window of 2 seconds and then try and forecast for 3 seconds. Not forgetting this is a very chaotic system. To be able to project forward a chaotic system, it's basically impossible, because if you try, you stop and you don't do any assimilation, you'll see that immediately, very, very quickly, your model will get further and further away from the real measurements, because we saw these two attractors and the system jumps around. And you can play with the observation noise and the background noise. I put values of 1 year. Okay. There are 2 different algorithms anyway. I just want to show you the quality of the results. This is very interesting. So don't forget that. So here, up to time step 40, I have observations. And then I stop the assimilation. And then from here on, all I'm doing is prediction based on what I have. So, okay, what are the curves? The black curve, solid black curve, is the truth. The black dots are observations. I only have observations in my observation window, right? And then I want to project, I want to make my forecast, like I'm doing the weather forecast, right? The initial guess, which is called the background solution, that's the dotted line. So you see very quickly the initial guess is getting far away. But if you look at the dashed line, which is the analysis, look how the analysis is staying close until about around here, about 90 time steps, extremely close, the analysis that I obtained from the 4D VAR to this chaotic system. This is something, if you try and simulate any chaotic system like this, and you have slight perturbations in the initial condition, like I had 20%, you'll see that very, very quickly your numerical solution will diverge away from the real solution due to the small perturbations. Okay, so there are three components, X, Y, and Z, and it seems to do a good job. And then there are improvements on 4D bar, which is called incremental 4D bar, which adds another step. And incremental 4D bar goes even further. Okay, so this is just to show you that in a very complicated chaotic system, the 4D bar using assimilation over a period from 0 to 40 time steps, like 2 seconds, can then project forward at least another 40 seconds. In numerical weather prediction, in the meteorological forecast, usually forecasts are done for 6 hours, and then after 6 hours there's a new forecast. So basically you assimilate over 6 hours, and then you forecast for 6 hours, and then 6 hours later you can do another assimilation. Because why 6 hours? Because to solve these equations it takes 6 hours for a very big meteorological forecast or regional forecast. So you see we can get extremely good results. And then just to show that it doesn't, oh, I thought I had something else. Okay, no, I'll show you after. Okay. So as I said, this is the variational part. The references are my book, the book of law. There are many other books written by meteorologists, written by atmospheric scientists, but they're often very applied to their own domain. And then one can see what's happening at the Met Center in Reading in the UK, but I give many more references on the website. Okay, so that was very briefly, but at least you have an idea of what's going on. Variational data assimilation. Now we're going to go to something that's even, I find, more interesting. Did I get it? Here we go. Which is what we can call statistical data assimilation. And statistical data assimilation is performed largely by what are called Kalman filters. Now, Kalman filter, why Kalman filter? Because the Kalman filter is an optimal filter. And we'll show you in what sense it's optimal. In fact, it's optimal exactly like the blue, like we saw before. It's the filter that gives you what gives you. It's the algorithm that gives you the optimal forecast taking into account, or the optimal compromise between the initial guess and the observed data, taking into account the noise characteristics. So I'll start an introduction. I'll speak about statistical assimilation in general, and then we'll show you that, in fact, the statistical assimilation is realized by Kalman filters. The trouble with the Kalman filter is that it makes a number of assumptions of linearity and other things concerning the noise. And if you want to relax these assumptions, which are quite strict assumptions, it's quite strict hypotheses, one has to go to filters that are nonlinear, and then the Ensemble Kalman filter and the nonlinear filters, of which there are three, which I won't go into, but just to show you that they exist, are extensions of the basic Kalman filter, which enable the extension of this method to nonlinear equations with nonlinear noise models and very complicated interactions between the noise and the system. Okay, and finally, I'll end up with some examples. Yes, okay, just one important remark is that today, most of the weather forecasting, for example, is being done by Ensemble Kalman filters. And people say this, Stuart, who wrote the book, and a couple of other things I refer to, I like a lot. He thinks that we can do a lot of other things, a lot of difficult problems in computational science can be solved with Ensemble Kalman filters. So it has the Ensemble Kalman filter is something that today is being used for various reasons. I'll show you very briefly. And it's starting to replace the Kalman filter, which itself replaced the variational data assimilation. Okay. Why for various reasons, these things. Okay, so statistical DA will generalize the variation approach to deal with errors and noise in the model, the observations, and the initial conditions. So now we're going to really have a more rigorous modeling of the noise. And in fact, Kalman filters can be derived from a completely stochastic approach, not stochastic, even from stochastic differential equations, which you'll see with Professor Marmory next week. So these are really making we're not assuming that a random system, a stochastic system, can be represented sufficiently well by what we call deterministic models, which the models we're used to are deterministic. There's no noise in reaction diffusion, or not usually. And if there is a noise term, then you cannot analyze these equations nor solve them using everything we've learned so far. One has to use stochastic calculus, which is much more complicated because the noise terms are very often non-differentiable. So how can you have a differential equation with a non-differentiable term? There's no, the solutions basically don't exist in a classical sense. So one has to define the solutions in using what's called the Ito calculus, which enables one to differentiate noise terms that are very noisy. So the statistical results, the variation can be a special case, and the statistical results, in fact, are just versions of the Kalman type filters, and there are many types of Kalman filters. Okay, and you can find a good mathematical description in the book of Stuart, for example. So what are we trying to do? We have two things. We have a noisy system, and this is a stochastic difference equation. It's not a differential equation, because you don't see, basically, if I took xk, xk and I subtracted, or I divide, you could see this is xk plus 1 minus xk divided by delta k equals mk plus noise. So you can see that there's a simple Euler, simple first order differential approximation, difference approximation of the derivative, which gives me this classical difference equation. But now the difference is I have wk here, and in the observation equation I have vk. So what are wk and vk? Well, these are stochastic processes, and in fact, which means stochastic process is just a random variable which can have, at each instant in time, can have another distribution. So we consider them to be Gaussian distributed random processes, with zero mean, because it's always easy to subtract the mean. So most analysis of stochastic equations is done with zero mean. And with covariance matrices Qk and Rk, so you can see the matrices can depend on k. In other words, they can depend on time. Okay, that's the whole idea. Is this is a very general treatment. So we have Wk and Vk. So we're representing by this the process or the modeling errors and the measurement or the observation errors. Okay, so we assume that they're independent, that the modeling errors don't affect the observation errors and vice versa. And that helps us to clean up certain cross terms. And we assume also that they're white noise processes, and a white noise process, by definition, with Yusuf, you'll see them next week, I'm sure, are characterized by Gaussian probability distribution. So just one question, noise model. So I said to you, it's not because we're mathematicians, we like Gauss, that we're going to force nature to be Gaussian. The Gaussian noise model is in fact the most general and the model with the least assumptions possible. All it says is that when we have a noisy system, the noisy system will usually have some kind of central value, which we observe most frequently. And around that central value, we have random variations. We're not sure if it's going to be 5 or it's going to be 5.1 or 5.7 or 2.8. But what we do know, what we suppose, is that as you get further away from 5, from the average or the mean, you're going to have fewer and fewer occurrences of extreme values. In other words, as we get further from the mean, it's less likely to have values that are much larger than the mean or much smaller than the mean. So all that Gauss says, the Gaussian approximation, all it says is that we have some favorite value that the system seems to be. That's the average value, if you like. If we're solving a differential equation without any noise, it's the solution of the differential equation without any noise. And then if we add noise, all we're saying is, well, it will usually be around that average value, but we can have fluctuations or deviations which are smaller or larger, but the smaller they get or the larger they get, the less probable they are. So Gauss is really the least constraining hypothesis. The Gaussian noise model is the least constraining noise model possible. I said it's thanks to Gauss who observed. He didn't say, well, here's the Gaussian distribution. Now I'm going to say that it's a good model for nature, anything in nature, any natural process. On the contrary, it's by observing natural processes that he developed the Gaussian function, the famous Bell function that we all use today. So it's a very, very good, a very efficient model for describing randomness, or what we don't know, even lack of knowledge in natural systems of any kind. So that's why when I put here WK follows a normal distribution with zero mean and QK, this is not really a restriction. It's not a restriction, it's a hypothesis, of course, but it's not a restriction because, in fact, it's nature that inspired this and not mathematics that's trying to force nature to be something else. Okay, so that's very important to notice. Very, very, very seldom we speak about the fact why Gaussian. Everybody says Gaussian, Gaussian, Gaussian. Okay, it turns out that Gaussian distributions have very nice properties. They are what's called linear probabilistic models because they're completely defined by two terms, the mean and the standard deviation. If you know the mean and the standard deviation, or the mean and the variance, Gaussian distribution is completely known. So you only need to know two quantities to define a Gaussian distribution. So it's a simple type of distribution, but it's not because it's simple that we use it. We use it because it's a good description. Okay. So Q and R are the covariance matrices, which we have to know, and they represent the modeling and the observation errors. There are a lot of assumptions about linearity, unbiased, uncorrelated errors, etc. They are not limiting because there are many extensions of a standard Kalman filter, which I'll show you very briefly afterwards. So the Kalman filter, which will be what will give us the optimal interpolation, if you want, has a number of limiting hypotheses, which I'll explain to you very, very shortly, but they can be generalized. Okay. Another thing that I should say is that in a broader mathematical sense, one should define everything starting with stochastic differential equations. Then all the theory of Ito provides, well, to a certain extent, a detailed solution to the problem of optimal filtering, because what we're doing is optimal filtering or optimal forecasting from given data, as well as rigorous existence uniqueness results. Okay, so you can find, there are a lot of books. I gave some references on stochastic differential equations. It's a whole domain which if you're interested, it's fascinating, but it requires quite complicated measure theory at some point. in order to solve these equations, okay? And then one can do this completely rigorously based on SDEs, but we won't do that. So you remember, what we're trying to do is we have a model of trajectory, which is the black line. We have observations, and we want to steer our system as intelligently as possible, taking into account the observations and using our previous guess, not to go too far, but not to stick to the observations either, as we'll end up with something that just follows the observations. We want something that will go smoothly between them, and that's the whole idea over time of the Kalman filter. Okay, so the Kalman filter is very easy once we've written it down. It's decomposed into two steps, which is called a prediction step and then a correction step. So you can call the prediction step the forecast step, and you can call the correction step an analysis step. So this will be the two major steps of statistical data assimilation. And then we will suppose that at time tk, obviously we'll start with k equals 0, we have the results of a previous forecast, and we have the results of a whole ensemble of observations. We have a number of observations in the vector yk, and then what we're going to do is that using these two vectors, xk and yk, we'll perform an analysis that will give us the analyzed state xak, and then we use the evolution model to take the state forward from time tk to time tk plus 1. And we will obtain the forecast, and then we just turn around. Once we've reached here, go back here and run through the loop again. So it's a basic predictor corrector type of algorithm. And what's great is once you have the Kalman theory, you can translate it into a very, very effective algorithm. I'll show you in a minute. So here you can see it all together, basically what's happening. Huh? So this is really, we've seen this already in variational data assimilation. We have an analyzed state. We predict forward. Here comes an observation. We do the Kalman analysis and we get a new, so from F, we correct to A, and then we continue with a prediction. That's the forecast. But the forecast is not good because it's far from the observation. We correct and we get XA, and this is how it continues. So this is all the idea at every step. We're going to make a correction which will be optimal in a statistical sense, and it's a generalized. So what gives us the optimality is the Kalman filter. It's something that Kalman discovered in the 1950s. The Kalman filter, it's famous because the Apollo, remember, Apollo was one of the first missions, I don't talk about the first mission to go to the moon. Without the Kalman filter, Apollo would never have reached the moon. So the Kalman filter, it really works. It's not just a fancy mathematical tool. It's really used. It really works. It's really used today. All our GPS and navigation systems are based on Kalman filters. Any type of autopilot, when you go in the airplane, when you take your flight, everything's been done basically with Kalman filters to a large extent. Okay, all the navigation, automatic navigation, is based on Kalman filter, and I'll show you why. Because in fact, once we've got the formulation down, we boil it down, it can be programmed in 9 or 10 lines, and these 9 or 10 lines can be put onto hardware, so they can, a very small microprocessor, a very small chip, can do a Kalman filter calculation extremely rapidly. So that's why it's been used, and that's why it's still used, and it's still the basis of all of our GPS and navigation systems today. And of course, okay, you can use it for weather forecasting and any other data assimilation problem. So let me just take this here. Okay, so basically, I won't go into too much detail, but Kalman showed all of this. I think that's the end of the page. Okay, so basically what we have here is we have our dynamical model, xk. Notice here that there's a linearization. I use a linear model, okay? That's one of the main defects of the Kalman filter, but the ensemble Kalman filter and the extended Kalman for the other nonlinear filters, which are extensions of this, take away. So I can have mxk function of, I can put parentheses around xak, but not in the Kalman filter itself. When Kalman defined his filter, it was 4 linear state space models of this type. But you see, I've added a second equation, and that's the equation for the covariance matrix. So not only do I project in time, do I evolve in time the state, but I also evolve in time the covariance, and that's the secret of Kalman filter. You're doing it at the same time, evolution in time. So I have a dynamic equation for the state and a dynamic equation using the same dynamics, of course, mk plus 1. And this is the model noise. So you see the expression for PF is obtained from the dynamics equation and the definition of the model noise covariance qk plus 1. This works extremely well. As I said, it got Apollo to the moon and it continues doing many things of that sort, just to show that very critical things. You can trust completely the Kalman filter, even though it's a linearization, because somehow you suppose that your dynamic system stays in a linear regime, that it doesn't go too far away from where it should go before we calculate the next point, and then it navigates and continues like that. So that the Kalman filter comes from that, and then what will happen is we're going to do some optimization. So you know, it's quite easy to follow. I won't show all the details. So at time tk plus 1, in fact, we know the probability distribution function. We need that to calculate a mean state. What we calculate, in fact, is the mean state and the covariance of that state. So we know the mean x, the forecast at k plus 1, and the covariance matrix pf at k plus 1. And we use the assumption of a Gaussian distribution, which means Gaussian distribution, as I said, one of its main qualities that it's completely determined by its first two moments. If you know the mean and you know the variance, in this case, you know the mean vector and you know the covariance matrix, you know completely the Gaussian distribution. So it's well defined, the Gauss. And then you perform an analysis step, which will correct this PDF using the observation we just received. And lo and behold, you won't be surprised, you see, what do we see here? We see exactly the same form of K. That's why it's called K, the matrix, in 3D var and 4D var, in 4D var, because it's the Kalman matrix. So the letter K is in honor of Kalman, who discovered this optimal matrix, but Kalman derived it in the statistical sense, in the statistical model, and not in the variation model. And then once you know K plus 1, you use it to project forward to get your analysis. And then once you know your analysis, xak plus 1, you can use, you can update, you can also do the analysis, on the covariance matrix. So we have an analyzed state and an analyzed covariance matrix. And these we put into a very, very simple algorithm I'll show you here. And this is basically, Kalman filter comes to this, and then I'll show you the algorithm. And the algorithm is exactly word for word. What I do is I write down 1, 2, 3, 4, 5, in 5 lines the Kalman filter using MATLAB or Python, which doesn't require. Okay. You can use matrix vector matrix notation. You can write a Kalman filter in it's 8 lines, okay, but because you have to initialize, etc., etc. So the Kalman filter is very, very efficiently programmed, and it follows exactly the steps of prediction and correction. So you start with an initialization, you do the prediction, and then you do the correction. We call the time update, and then the measurement update, and all the calculation is you compute the Kalman gain, you project forward, you update the state, you update the error covariance, and then with the updated error covariance, the updated state, you go back here, you project the state ahead, you project the covariance ahead, and then you correct again as soon as you get your measurement. Okay, the measurement comes in from the H. That's the measurement vector. So this is how the Kalman goes from measurement to measurement. So there's always instruments measuring. You think of an airplane or a space shuttle, something, whatever, or a space vessel. It's got instruments, it measures, it knows where it is, it measures, it has observations, and it corrects the trajectory to reach some desired point. So that's basically how it works, and then it's very easy to... Okay, so basically, if the a priori, the background data and the observation data, then Bayes' rule also can be used to compute, and then the posterior will be Gaussian, and the parameters are given by the blue. Okay, you can relate all of this to Bayes' theorem also, and we've noticed that the cost function is exactly the same as the one used for 3D var. So that's the consistency between the variational approach and the statistical approach. So I won't go into many more details. I just want to show you, I think, basically. Okay, there are some issues about the error covariances. They play a very important role, and a good specification is necessary for the quality of the analysis. So there's a lot of experience, a lot of research done on how to correctly specify background and observation covariances, and there are different ways of correcting when they get too small or when they get too large. Okay, and then the correlations are important because they specify how the observed information will be smoothed in the space of the model if there's a difference between the model resolution and the observation density. And the model error covariances can also be important, just as they are in 4D VAR. So there's a lot of work to be done. Okay, then one of the shortcomings of the Kalman filter is that it requires linear dynamics, so that's one of the main defaults. And another thing is that it supposes that the noise is Gaussian and that it's additive. We have additive noise. You saw that I added the noise to the equation. But in a more general context, the noise can be multiplicative. In other words, we can have a system where we multiply the state by the noise, and it's not just added, or we can have additive and multiplicative noise. So people who study stochastic differential equations know that one can have, though most of the analysis is done with additive models, there's also analysis that can be done with more general models. And to cover these extra cases where the dynamics cannot be so cleanly separated, saying I've got a linear model, mk plus 1 times xk plus 1 plus wk, but I can have m function of xk plus 1 plus, well, multiplied by wk or plus something else. And in those cases, and if the noise is not necessarily white, we can have different types of noise. This is supposed to be white noise. You can have what's called colored noise, then the noise model becomes more complicated. We need to extend them. So one of the most important extensions of the Kalman filter is called the Ensemble Kalman filter. It uses an ensemble, in fact, a set of realizations to compute estimates of the population mean and an estimate of the covariance. So we don't, you'll see that we don't have to compute the covariance by inverting the Kalman gain matrix like before, but we can estimate the Kalman gain matrix by taking suitable means and variances over a whole set or an ensemble of realizations. That supposes that initially we can generate an ensemble of realizations, but we perturb certain characteristics of properties of the parameters randomly, and we calculate 20 or 30 or 40 or 50 realizations, and from that ensemble of realizations we can calculate all the statistics and all the matrices that we need for the Kalman filter without having to do the inversion of the matrix. So several important remarks here. The NKF avoids the linearization step, which is the basic step of the Kalman filter. The ensemble filter doesn't have this m multiplied by x, or mk plus 1, xk plus 1. It also avoids completely the inversion of potentially large matrices. We saw that to calculate the k, we have to invert matrices. It doesn't require any adjoint, which you would require for 4D variation and assimilation, which can be quite costly and quite complicated. And as a result, the NKF is really applied to a huge number of real-world problems. So the NKF is a very, very popular extension of the Kalman filter, and it works in the following way. It basically works in the same way. You'll see that one initializes by generating with it. The only difference with the basic filters, the Kalman filter, we just had one initial state. Now we need m initial states, which we call random states. They're obtained by random perturbations of one of the parameters or the initial condition, or condition, usually by perturbing the initial condition. So we hope to have some kind of representative initial ensemble of states, and then we compute the prediction for each member of the ensemble. So we just project forward, and there we can use nonlinear. There's no need to use linearization because now we can use a fully nonlinear model. I'll show you with the equations. And then, as usual, we do the analysis, we do the correction. That's the prediction, correction, forecast, prediction, correction, analysis, correct the prediction taking into account the observations that we've just obtained. So a couple of notes here just to show you why the ensemble Kalman filter is so great is that, okay, this is not very important. This is just information. You can perform the propagation at the end of the time step, or end of the analysis, the beginning of forecast. That's really technical. But what's important is that the Kalman gain is not computed directly by inverting these matrices that I showed you before, but it's estimated from the statistics of the ensemble. Because we have an ensemble, we can estimate the Kalman gain explicitly. And with the exception of the Kalman gain computation, all the operations in the ensemble members are independent. And as a result, the computation can be parallelized. Now, you know that we speak a lot about parallelizing because now we have, even in your laptops, you have a number of processors. In bigger computers, you have many, what they call cores or many CPUs. And the advantage of the Kalman filters, if you want to have 50 members, you can compute one member per CPU. So you can have 50 CPUs or 50 cores, what we call cores today, each one computing the Kalman filter. And as a result, the method is becoming extremely popular due to the fact that it's parallelizable. Okay, in small problems it's not really important, but when the problems get large and everybody, here there's 4 processors, and in new laptops there are 8 processors or the 8 cores. This is one of the reasons for the huge success of the Ensemble Kalman filter. It's parallel nature, because you're generating independent realizations, and each realization you're letting it evolve. You're sending it, you're predicting and you're predicting, but each one is independent of the other, and then you only need to bring them together when you want to estimate the Kalman gain, the K, which requires an estimation. So I'll show you more in detail in other steps. So basically it looks like this, okay, but don't worry, even though it's a bit more, it's more complicated than the Kalman filter. The Kalman filter is very easy. I'll show you an example to program yourself. And Ensemble Kalman filter, usually one takes software, open source software that's available. And basically you can see, if you look very carefully, you initialize the ensemble, you loop over time, and then for each time step you have to generate your observation, or you generate your observations, and you compute here. I'm computing the ensemble mean, so I'll compute X bar and U bar, which the U bar is just for the observations. I calculate the mean of X, of my state X. I calculate the mean of my observation, and then using these mean values, I can calculate an estimation for K. You see, K is the Kalman matrix. The only thing I have to invert is YF, but Y, I told you Y is of small dimension. It's only the dimension of the observations, not the dimension of the state, so it's a much easier computation. And then once I have my Kalman matrix, then I can loop over the members of the ensemble and do the analysis, which is XF plus the K, Y times H. This is the classical update, where I update taking into account the observations that I've just received. And then once I've got X, A, I, K, I can calculate the next forecast. And the next forecast is used as the initialization of my next time step. The K at the top is the time steps, right? And inside I have to do all this work. But as I said, the advantage is that this work can be largely parallelized. And so it gives an extremely efficient filter where there's no hypothesis whatsoever. You should see it. Did I put it in here? Yeah, you can see. I'm using completely nonlinear, but there's no hypothesis like the classical Kalman filter. The classical Kalman filter would have a linear matrix M times vector X. Here, I've just got the operator M, which can be Navier-Stokes nonlinear reaction diffusion, whatever you want, multiplied as a function of the state. So it's a very, very, very general, mathematically very general algorithm. Okay, I won't go into it, but of course, because it's been used for many, many things. There's a lot of work been done on variance of the NKF. So the classic book, the guy who invented the Ensemble Kalman filter, his name is Evensen. He's a guy who works in Norway, and he has a complete book just on the Ensemble Kalman filter. Okay, in my book on DA, there's a chapter on the Ensemble Kalman filter. Okay, and then there are many, many variants. I won't go into them, but many. And people are continually improving in certain contexts. Certain modifications are necessary. It depends on the type of application you have. But usually one starts with a classic Ensemble Kalman filter, and if that doesn't work, one can eventually go and look at one of these other filters, which are just modifications of the Ensemble Kalman filter. Okay, but that's the ensemble. Then one can go much further, and we can develop a much more general filter which can deal, okay, with the major shortcomings. That's a nonlinear process and a nonlinear measurement operator. And then we have a more general form. And then we can even, I haven't done here, but we can even have, you notice that both the dynamics and the observation are completely nonlinear. And to deal with these, one can formulate nonlinear, we can have nonlinear functions, and we can formulate extensions of the Kalman filter, which go under the name of Bayesian filters. And then if you do it in the framework of Bayesian filters, it's very easy to derive all these nonlinear filters. There's a very, very good book that's available by Simo Sarka. That book is free, it's open source. You can, if you type his name and you write filtering, Bayesian filtering, you'll find he has 2 books that are very good that I like a lot. Very practical books. One on he even has a book on solutions of statistical differential equations, and then he has a book on Bayesian filtering. So he derives all of Kalman filtering in a much more general theoretical framework, which is called Bayesian framework, which enables you very easily to derive linear, which is the Kalman filter, and nonlinear, and ensemble methods, nonlinear filters. It's a very, very good book. He has 2 books in fact. So anyway, they are nonlinear filters. We don't have time to go into them because I want to show you some examples. So there are 3 basic nonlinear filters, which sometimes with the ensemble Kalman filter might not work well enough because the noise model and the observation model are still linear. And then one can use what's called the extended Kalman filter, which is a linearization of a nonlinear filter. And then the UKF is a special linearization. The particle filter is the most general filter, which doesn't assume any linearization anywhere whatsoever. So it's a completely nonlinear filter. And so, okay, so I'll show an example of a nonlinear filter, but in real applications, we usually have nonlinearity in the model and in the measurements. And in addition, the noise is not necessarily additive. We've always assumed plus WK, but in reality, sometimes the noise can be multiplicative. In other words, it multiplies the state. It's mx times W instead of mx plus W. So this additive noise assumption can sometimes not be valid in very noisy systems, and we still want to be able to navigate. And where there's a lot of turbulence, you want the plane to get to its destination, right? So there's a lot of noise. And so you want to be able to deal with very nonlinear measurements also, and non-additive noise. Okay, then one of the ways, as I said, you linearize about the current state, the current mean and covariance, and you gives you what's called the extended Kalman filter. This is one of the favorite filters also, which has a better performance in nonlinear situations than the Kalman filter. And as I said, the EKF, the extended Kalman filter, is actually today's standard in all navigation and GPS systems, for example, which have to steer their way through noisy environments. The EKF is used today. So, okay, I won't go into it, but basically the difference is that here you see I start with non-linearity there, and here I haven't done the multiplicative noise case. And one uses Gaussian approximation. Okay, that's classical. And then we have to get first order truncation of a corresponding Taylor series to get the linearization of our equation. And we obtain, so I'll just show you what we get at the end. So here, it follows the same steps as before. There's initialization, there's a prediction step, and there's a correction step. But the only things that I haven't defined, you see I use mx here, mx, and here I use hx. So mx and hx are linearizations obtained by first order Taylor expansions, and truncating at the first order. So it's a true linearization attempt that I do at a first order Taylor expansion, and I throw away the quadratic terms and higher. So this is the true linearization, even though I calculate m hat, where do I use m hat I use here? I can use a truly nonlinear model here, but here I cannot use, so I use a linear approximation. And that gives the extended Kalman filter, which we can show performs extremely well. And then there's an updating as usual, and just by definition, mx, it's just the Jacobian matrices, because we're dealing with matrices and though we're dealing with vectors, so we're differentiating with respect to vectors, so we end up with a Jacobian matrix, and we evaluate at x equals m. and here at x equals m, and we get the first order linearization of these nonlinear terms mx and hx. State operator and the dynamics and the observation. Now it can be purely nonlinear. And then we can have nonlinear also with non-additive noise. You see here I've taken a completely general. M is a function of x and a function of w. That more stochastic than that you cannot do. In fact, in terms of stochastic differential equations, this becomes quite complicated to analyze. Usually when one does SDE, stochastic differential equations, one treats the case of additive noise because this becomes theoretically quite complicated. Okay, there's some necessary modifications to take into account functional dependence on W and V, but just to show that these extended Kalman filter, which is a linearization of the nonlinear system, can deal also with multiplicative noise, which is not the case. It's not the case for the usual Kalman filter. Okay, to finish. Well, anyway, I won't go into this, but there's a lot of advantages and disadvantages, but this becomes quite technical, why one should or shouldn't use an extended Kalman filter. But the bottom line is that it's a very solid filter, and as I mentioned earlier, it still remains the basis of most GPS and navigation systems, and you understand these are very critical systems. If the EKF didn't work well, you wouldn't be able to find your way, and your flight wouldn't arrive at the correct destination. Okay, so this is good to know that there's an EKF, and you've seen it, right? So now you can say, but I know what's going on behind there. There's an EKF, and the EKF, good math, so you should get to the destination. Okay, so let me show you a quick example, which is a very, very simple case, which shows how the Kalman filter works. I'm going to take a scalar case, because a scalar we can actually compute everything by hand. Okay, it's called a Gaussian random walk. So it's the most simple dynamic system that you can imagine. You see xk equals xk plus 1. So my dynamic operator, its identity, it's equals 1 now. So it's the most simple, but there's dynamics there, right? But it's just the dynamics are equal to 1 now. My state equation is 1 now. Xk equals xk plus 1. But I add the noise. And then, of course, I have my observations. Y equals xa plus vk. Vk has a Gaussian distribution. Wk has a Gaussian distribution with Q and R as before. So this is not really a great system, but it's very basic, and you find it in many applications. It represents any application where you have a slowly varying quantity that we measure directly. We have process noise, Wk, taking into account fluctuations in the state, and we have measurement noise accounting for measurement or instrumental errors. And the objective of these is always to estimate the state xk over time, taking into account the measurements. Okay, that's always our objective, and we want to do it in an optimal way, and we know that I've shown you that the Kalman filter is an optimal filter in the true sense of optimality. Okay, so all I have to do is to write down the 3 stages of the Kalman filter: initialization, prediction, correction. It's very easy. I showed you the five equations. You just take those 5 equations, you write them down, and here we can write them down. So I can do the initialization, that's what, just M0 and P0. I can do the prediction. You remember predictions, the MK equals big capital M times M, but capital M equals 1. So MK hat is just MK minus 1. And then I can project using the state equation, or the dynamics equation for the covariance matrix, MK, PK plus QK, but MK equals 1, so it's just PK minus 1 plus Q. Okay, because I've assumed here that Q does not change over time. It's time independent. So that's already my prediction. And now I have to do the correction or the analysis. So I have my measurement, dk, I calculate its error. H equals 1 in my case also, which I just have the measurements, yk minus m hat. And then I calculate the denominator. This is just the denominator of the Kalman of the Kalman update. So that's just the denominator. So, and I can calculate using dk, using the previous pk, sorry, and using rk, I get sk, which is the denominator, and I multiply it by the numerator, pk ht. In this case, h is equals 1, so I just have pk times s inverse, okay? And then update, mk equals the previous value plus kk times d. D, you remember it's y minus hm, and I update also my covariance matrix, how I should do it. And here, because S is just a scalar, I just have P squared divided by S, and that's my update. So there I have the complete Kalman filter defined, and I can write it up. So all of this at the beginning, this is Octave or MATLAB code, or anyway, whatever, you can write it in any language. This is all just initialization, and this is just generating the random measurements here. Okay, and then here, the actual Kalman filter itself is just this little part here, and I'll show you. I've repeated it here. Okay, the Kalman filter itself, it's exactly what we've seen. You just take the formulas, the equations, M, that's my dynamics equation, update of P, here comes D minus HM, that's my innovation, because I got the measurements that come in. I calculate the denominator S, HP H transpose plus R, and K equals PH divided by S, or S inverse P times H. Once I have that, update, and then just to end the loop. So basically you see I've got 1, 2, 3, 4, 5, plus the update 6 lines, and the Kalman filter is completely, and you say, well, okay, does it work? Well, it works very well. So this is just a Gaussian random walk, so it's something very noisy, you know, it goes all over the place. It's very noisy. I'm sure with Yusuf, you'll simulate some of these simple processes, and here you can see the state is the solid blue curve, measurements that arrive are the red circles, and the Kalman filter estimate is in green. And then I've put 95% quantiles around, so I've got a confidence interval, if you like, of 95%. And here I've used fixed values of Q and R, but you can also play around with it. The codes are all available, and I'll give the reference at the end. On one of my web pages, you can get all these codes to do this. So this is a very, very basic Kalman filter, but as I said, it's the basis of a lot of interesting stuff, and it shows you how the Kalman filter, in spite of the fact that we have noisy measurements, the Kalman filter seems to follow quite well and doesn't deviate around too far from the true state, which is the blue state, which I'm trying to find. I don't know the blue state. All I have are the measurements. I just put the blue state as reference. What I know are the red circles, and I find the green curve. So you see, I can find a very, very noisy result just using the Kalman filter, right? You understand the blue curve, I don't know. I just used the blue curve to generate the red points, and the Kalman filter only knows the red points, okay? Knows the red points and gives you the green line, which looks quite good. Okay, simple. Now I'll say, well, okay, that's very simple. What about the Lorentz system? So let me take the Lorentz system with some noisy measurements and try and do Kalman filter on it, okay? So what I'm gonna do here, it's a twin experiment. Okay, twin experiment means I just used the Lorentz system to generate my measurements, my observations, okay? The observations are the green circles again. Well, I've changed colors, yeah, the green circles. So I've got observations only up until time 2. And then I'm going to let the system go free, right, and see what happens. So here you can see that the background, if I did nothing, the background solution is the orange solution. But look what happens. The true solution is the blue, right? And my analysis, the output of my Kalman filter, have a look. You see, that's amazing, huh? It sticks with the true solution, whereas anything else would deviate very, very quickly. Huh? This is a long assimilation window where I have no more measurements. I only had measurements for 2 seconds, and I'm doing a really good job. Yeah, there's small differences here, but not that much, with the Kalman filter. So the Kalman filter is assimilating a noisy aquatic system with noise. Okay, so it's not an easy problem to solve, to predict without any information. And just using a simulation of 2 seconds, I can predict for it quite a way, whereas if I hadn't used the Kalman filter, very quickly you can see with the orange, the background solution, which is without the Kalman filter, would start to deviate and get very, very far away. So fortunately, the Kalman filter is helping your flight navigators. Just, okay. But you can imagine if we want to predict the trajectory of something else, a virus, an epidemic, if you have something over time, you can see that in a noisy situation, the Kalman filter does an amazing job. And then you can go much further, okay? what I say, it does a remarkable job. No evidence of filter divergence, even though there's some ill-posedness of the system. We begin to see a slight phase shift around t equals 8, but usually by the time you get to t equals 8, you already have new measurements. Huh? So I'll go back to the green phase right here, the shaded phase. So by around t equals 8, I'll surely have new measurements that will come in, and then I'll be able to rectify and then start again predicting and have a very good prediction. So we get predictions that are much more reliable than if we didn't have this Kalman filter. So the filtering and the data filtering. The data assimilation, what we call statistical data assimilation, using an optimal filter, which is the Kalman filter, gives us extremely powerful prediction capacities. Huh? Okay. So let me just show you. So you say, okay, that's an ODE, but we can do that for a very complicated PDE, which is known as the chaos of the Kuromoto-Sieraszynski system. Oh, here it comes. Okay. This is a model that's used for complex, what's called complex spatio-temporal dynamics, in particular for simulating turbulence. Okay, quite a very fourth order here, and here's the nonlinearity. It's a fourth order equation. It looks, you know, like you don't want to solve this equation if you had to, but we have to, right? So what's amazing is that one can set up an ensemble Kalman filter for this. Okay, sorry, let me go back then. Okay, so chaotic behavior is obtained for a certain value of nu. It's like the Lorentz system for certain parameter values. It exhibits chaos. UXX term gives instability at large scales. The dissipative term damps at small scales, and the nonlinear term, it's exactly the same ones we find in Burgers or in the one-dimensional Navier-Stokes. Transfers energy between large and small scales. It's a very, very complex model which captures a lot of physics, which is used mostly in turbulence modeling. And what's amazing is that the ensemble Kalman filter, here's the true trajectory. Here's an ensemble Kalman filter which is obtained from noisy measurements, and you see the difference is reasonable. It's not very small. Let's say it's about 0.5 over 5. It's approximately 10% error, which is really not bad, which is not deviating a lot. That's at a certain time. I don't know what time. I don't remember what t. Oh no, that's t on the. Sorry, that's t and x. Yeah, t and x. Oh, the unknown. Yeah, okay. It's a snapshot of the solution surface in the xt plane. Okay, because it's a two-dimensional. Well, one dimension in space and one dimension in time. And if I look at cross sections, if I take those previous things and I cut them across to see what I'm doing, how I'm doing, then you can see that as once again the red points are the observations, the black is the true model, the background solution is the blue. So immediately it starts going crazy. The background solution is good for a little while, and then immediately it starts deviating. Okay, that's at different cross sections at x equals 5. That's u at x equals 5 at the 15th point and at the 35th, what x equals 35. So you see very quickly, if I didn't have the Kalman filter, I would start moving away from my solution very quickly and end up with something completely different. But thanks to the Kalman filter, which is the green one, have a look. It's amazing. The Kalman filter sticks to the true solution and doesn't move. Huh? And it's a very, very complicated, nonlinear fourth order PDE with chaotic behavior, etc., etc. That's just to convince you that these filters are really extremely. And then just a very last one, very quickly, I'll show you how we do a nonlinear filter, a truly nonlinear filter, which is the EKF, the extended Kalman. This is the guy that's used for GPS and navigation. Okay. So a common model that we know very well is oscillations of a noisy pendulum. So there's a pendulum which is oscillating, but there's noise, there's WT. This is d2 theta dt squared plus g over L sine theta that gives us oscillations of a pendulum. This is a noisy pendulum, okay? And so we can write it. We've added WT, which is a white noise process. So we can write it in state space form, x dot plus mx plus w. And you have, just to show you, here's the x, it's theta theta dot. mx, it's x2 g over L sine x1. So this is a nonlinear part of m. As you can see, it's m function of x and not m times x. So there's no way, unless I linearize, huh? Okay, but I don't want to linearize the equation. I want a truly nonlinear equation. And w acts on the second component, so it's 0w. And then suppose we have discrete noisy measurements. Okay, with the horizontal component sine theta. Then we have the measurement equation, but here it's a scalar equation just to make things more manageable. And it has its own noise term, Vk. There's always noise in the measurements. And the system is thus a nonlinear in state and measurement, and the state space system is of the general form, what we saw before. And then you can use a very simple Euler's method discretization. And the matrices here have, maybe you'll see this, it's a very, very simple first order method for solving ODEs. Numerically, it's the Euler method, and you can see my matrices x, m of xk minus 1, and h of xk, which are, they're all nonlinear. And then I just want to show you the results. Okay, the noise term, we suppose they have Gaussian distributions. And there's a little complication here I won't go into. There's a process covariance matrix Q, which has to have a certain model. Okay, don't worry about it. It's something that when you know how to do, you do it anyway. You have to suppose some kind of dynamics for Q in order to get Q in the correct form, but I won't go into that. It's a little bit more complicated than in the simple case. And then what I do is that I can write the first order extended Kalman filters. I can also go to higher orders if necessary. Huh? So I need the Jacobian matrices, okay, to evaluate at x equal mk minus 1 and x equals mk. And it's quite easy here to find dm dx, because you've got the equations. You just have to differentiate, and obviously you differentiate sine and you get cosine. And when you differentiate the measurement equation, it's also sine, you just get a cosine there as well. So we have the linearization that we need, and then I can do simulations, and I'll show you the program. So in the simulations, the state is solid blue, the measurements are red circles, and the EKF gives a green curve, and I'll show you what happens. So you see, have a look. I've got noisy measurements, and they're quite noisy. I didn't take the noise extremely small so my thing would work, right? So initially, of course, the blue curve is the true curve, which I don't know, right? All I have with the noisy, all the Kalman filter gets are the noisy measurements, huh? Okay? And it has a model of the system, okay? And so you see initially the green curve, it's quite far away because the first guess it cannot get, it needs more measurements to get close to the system, but very quickly you see it approaches the blue curve and it sticks with the blue curve, it doesn't move, huh? Well, a little bit. And that's a nonlinear system also with using a nonlinear model based on the extended Kalman filter. And the code, okay, it's nothing. The code, if you go back and look at the formulation, the equations that I put for the code, you see it's exactly the same. Here's M, the matrix M. Here's dm dx, that's the Jacobian. And then that's the covariance matrix. Here's the measurements coming in, and here's h of x, and I calculate the denominator of the Kalman gain. I calculate the Kalman gain, and I update and turn around. So this is the guy that's programmed in the chips, in the hardware that does GPS and does navigation systems, among other things. And of course, I just tell you that to show you that it's very efficient. It can be computed extremely rapidly with very, very limited hardware, and it does an extremely good job. Okay, so all the code for the examples that I've shown you here, you can get them from my website or my GitHub. It's my GitHub site. So I have a Git which contains all the codes. It contains a lot of other codes. If you go up 2 levels, you get to my website, DTBX-V1. You just stop there. You'll see there's a tab with codes, and in the codes I have a lot of other codes, which are all the codes that are used in my latest book. Because you're welcome to go there and take whatever you want and use whatever you want. On the contrary, you should go there and take whatever you want. So for a lot of things, I have both Python and Octave codes. Some things only have Python, some things have Octave. And I have a lot of machine learning stuff and other statistical analysis, which is mostly done in R, but sometimes in Python as well. So there's a lot of code available, which is code I've been using to teach. So it's really teaching material. It's well explained, and don't hesitate to go there. And that's the list of references. Okay, thank you very much.